All right, we're going to change gears a little bit here. Now what we're doing is going to be actually students usually find this pretty interesting in that we're going to be doing what structural design engineers themselves would do. A whole bunch of the stuff we've looked at before. We've looked at a lot of rectangular timbers to be used as beams. We've looked at certain built-up timbers. We looked at box beams and some I-beams that somebody make by nailing a couple boards together. Now we're going to actually do what most structural engineers would do, which is specify the limits on the problem, which is the span of the beam and the expected load on that beam, and then essentially go to a catalog and pick the appropriate beam that's already manufactured. It's a lot cheaper that way. You don't want to do a bunch of one-off design to try to keep the cost of structures down. That's why I asked you to bring your book today, because we're going to be using the beam tables right in the back. We'll be mostly concerned, at least today, with bending stresses and shear stresses, the two big ones that we've looked at for the most part in just straight, standard structural type beam applications. Torsion can be a problem in some ways in certain type of building applications, but for the most part we're mostly concerned with bending and shear. And it's the bending that normally dominates the design. Shear can be a concern and should always be looked at, but it's generally bending that is the big concern, and it's also the bending that dictates the design of the types of beams that we're going to be looking at. All right, so let's go back to our bending equation, where we found the normal stresses in simple bending due to transverse loads. And if you remember, that was MC over I. There was a minus sign in there, but tradition dictates that we just take the minus sign out, and by inspection you pay attention to whether this is a compressive stress or tensile stress that's expected. For steel, it's not a big concern. Steel is pretty much the same in bending, in compression as it is in tension. But for wooden beams, it's very much a concern. There's like an 8 times difference in most woods between what a wooden beam can take in compression and what it can take in tension. Very, very weak in tension in general. So we're going to change up the look of this a little bit. We're going to define what we call the section modulus. I'm not sure why we didn't do this right from the start, but our author chose not to, so I chose not to. We're going to define the section modulus, big capital S there, defined as the cross-section moment of area, first moment of area of the beam, divided by C, which, if you remember, is the greatest distance in the beam from the neutral axis. That, of course, makes this then M over S. So if we need to reduce the stresses, we need to increase the section modulus. Greater S gives us lower stresses. Notice too that section modulus is purely a matter of the beam's cross-sectional geometry. It has nothing whatsoever to do with the load. It's the M part that's the load, and the S is entirely geometry. And there's no reason we couldn't have done this right from the very start when we first came to this bending equation. But for some reason our author preferred that we not do that. So he's got a lot more experience teaching this than I did. So we'll follow his lead and introduce it now. So let's take a quick peek at the type of thing that can do for us, just so we get familiar with it. We'll just do it real quick for two rectangular beams. A 6-inch by 4-inch beam, and then one of the same area, and thus the same weight, a 3 by 8 beam. So we can figure out the section modulus real quick for either of those. We'll just label them for convenience. Remember, I is 1/12 BH cubed when in that configuration, when we're taking the neutral axis to be horizontal as we look at it. And then C, of course, is just the distance from the neutral axis, which in this case will be right down the middle, to up to the middle part, or up to the edge part. So we can calculate it real quick. It's just a matter of putting in those numbers. In fact, S actually reduces to 1/6 A times H, just to make things even speedier. And they have the same area, and so we can compare the section moduli for these two beams, just to show that even though the area is the same, the weight the same, the amount of material is the same, the section modulus is substantially different between the two. So for this first one, I believe it's 24 inches cubed. Has units of volume, but remember it's not. It's the first moment of area. Actually, inches to the fourth. Oh no, section modulus has units of length cubed, squared, and then one more. And for this other beam, it's 32 inches cubed. So if you're trying to avoid bending stresses, then the much longer, much skinnier beam is the one to apply. There are other concerns when beams get loaded and transverse, ones we don't look at. They can twist under that load. We haven't really looked at that. It's not uncommon when using a long, skinny beam like that as floor joists, as you might on a deck, to stabilize those beams somehow. Either put some cross pieces like that to help keep those beams from twisting sideways in a way we haven't looked at, or to even put some kind of board just across there, just to stabilize that board. If you go get one of the meter sticks, especially the 2-meter ones, lay them on edge like this and push down on it, you'll see that it'll twist sideways a little bit in a way we haven't looked at. But for pure bending, this is the superior of the choices to take, even though the weight's the same and the cross-sectional area is the same. We know that to mostly be a factor of increased I, because there's a lot more area a lot farther from the neutral axis. Something go wrong up here?
Is that delta H up there?
Okay. That's AH.
Oh yeah, no. The area, cross-sectional area times H. Okay. So let's see how beam designers then apply this. It's easy enough to do it for rectangular beams, but most major construction is not done with those, so we'll do it with other structural beams. And if you look in your book, if you brought it, if not, you can look up here. In the back of the book are the geometric properties of structural shapes. This means then various I-beams, channel beams, L-beams, more I-beams, and we have it in both, at least in most of our books, SI and in English units. So what you see in this table, a description, this is sort of a catalog number of the beam, and I'll explain a little bit better. Well, you can see what these numbers mean, inches and pounds per foot. So the second number is actually the weight of the beam. The greater this number, the heavier that beam is. It can be that you pick a beam that's so heavy that the calculation for bending needs to be increased, because now you have the weight of the beam in the problem that might be significant. Then you have to refer to this little diagram there, what all the other columns mean. For the most part, the first number over here, remember this is the pounds per foot, this first number, this 24 for example, is basically the width of the beam, give or take a little bit. And it's fairly easy to remind yourself of that. If you look here at the table, you see a 24 there, and you look over and you see, oh, I think I said the width, it's the depth of the beam, which is basically the first number. You see, for the most part, they are all in agreement there. So it's this dimension on the beam, the depth of the beam. All right, so keep those handy. We'll start a problem here, and I'll show you then how we use these tables to actually decide which one of these beams is the better to use for a particular problem. So we'll take a very simple setup. We've done this before. A cantilever beam of some kind and an expected load of 15 kips on an 8-foot beam. So we know from having done this type of thing before that the maximum expected shear is 15 kips, and that's constant across the beam. You can almost do the shear moment diagrams in your head for something, a setup this simple. And the maximum expected moment will be right here at the place where the beam meets the wall, because that's where the force has the greatest moment arm, and that of course then is the 15 kips out at an 8-foot moment arm, so the bendings, or the maximum moment we expect right there at the wall, which is no big surprise if you, well, you remember probably as a kid when you go and stand out on the end of a tree limb, it breaks back here, it doesn't break where you're standing because of the greater moment arm. You were probably doing that calculation as you fell to the ground. I'm sure I know I was as a kid. Finish the calculation. If you take a good bounce, you get a little bit more time that way. So I believe this is 1440 kip feet as the expected moment. Now let's say it's a steel beam with an allowable stress of 24 KSI. That allows us then to calculate the section moment the section modulus by simply putting in the maximum expected moment over this allowable stress. That's just the bending equation, the stress equals mc over I solved for the section modulus that now allows us to find the minimum section modulus. Finding the maximum will overprotect the beam and quite possibly be too heavy itself and too expensive. So we want to find the minimum section modulus that will allow us to protect for this beam. And then there's, at various problems, various stages, the application of factors of safety. So we've got an expected moment, maximum moment of the 1440.
Kip inches.
No, that's kip feet. We'll need to fix the units, yeah, because this is kips per square inch. Is that kip inches? Oh, okay. Yeah. See, I don't pay attention to my notes because I'm not sure you guys are paying attention to me, so it's a way for us to check. Okay, there we go. Kip inches, so the units are already okay. Thank you, John. And that gives us an expected section modulus of about 60. Looking at the units, then we get a section modulus of inches cubed, just like we'd expect it would be. So we go to Appendix B, and we look at various beams that give us at least that section modulus. So the section modulus here, notice it's for two different axes, two different directions. The x and the y has to do with the standard ordinal directions there. And our neutral axis is in the x direction, so we look at the x-axis section modulus. And we go down until we find a couple that are just barely above the 60. So here's 68.4, but we wouldn't want the 57.6. So we'll put down that beam on our list, the W1840. So we make a little list as we go down that table of those beams that look kind of yummy. So the W1840, go down a little bit farther. Remember, we're going down this section modulus in the x direction. So we got that one beam, go down and look at some others. Here's 72.7. We don't want the 56.5, it's too small. So we'll go to 17.7, we got a W1645. Go look at a couple others. Where's our S cone here? So we go down a little bit farther, there's the 62.7, but we don't want the 54.6. It's too small a section modulus. So W1443. And this table in the back of the book is nothing more than the standard tables that the beam manufacturers are going to use. So you can look down this table, you can call them up and say, I need 2,000 W1443s for the building I'm putting together. Can you give me a bid on them? And so we've got a couple good candidates. What we see is that remember, this is the linear weight of the beam, this second number. So all three of these that we happen to pick out, you can pick out as many as you want, as long as they have a section modulus just above the 60 that we calculated as our minimum. We can see that this one is the lightest. So for our purposes in this class, that would be the one to pick. Other considerations would be cost, availability, other concerns that the designers might have, but for our purposes, we're just looking to make sure that we maintain the integrity, physical, mechanical integrity of the building, and so we'll just check this. One last thing we need to check is then the actual beam weight. This is 40 pounds per foot. We need 8-foot beams. So we see that that's going to add per beam about 320 pounds compared to a load of 15,000 pounds. It's not a big concern. There are times where the load is increased significantly by the weight of the beam itself, and so you just need to go back into the calculation. If it was a concern, we'd now add a uniform load here that represents the 40 pounds per foot and redo the calculation to find out what the maximum expected bending is then. The weight would be taken as a uniformly distributed load. And that's it. That's the game of selecting a particular I-beam of interest for a particular problem. So let's apply it a little bit more. So simply supported beam, as we've looked at before, with this kind of loading for about 60% of it, we have a uniformly distributed load, and then a point load at the middle there. So this is 3 meters and 1 meter on either side of that point load. Okay, 20 kilonewtons per meter and 50 kilonewton on that load. Now, you don't have to draw the shear moment diagrams, but we do need the maximum shear and moment to be able to calculate the appropriate section modulus, because we need to protect for the worst possible situation on this beam, not just some average value. So we need the maximum shear and minimum, maximum shear, maximum moment. All right, just to help things a little bit, I'll give you these 52 kip and 58 kip, just to speed things up a little bit, and then we can figure out what the maximum shear and maximum moment are. Oh yeah, kilonewtons, sorry. Of course I mean kilonewtons. I wouldn't screw up the units twice in one day. How dare you imply that, Tom? Okay, thank you, good catch. One person's awake, and it ain't me. All right, we can figure out the shear moment diagrams. We know that we're going to start with a shear of 52 kilonewtons there and come down at the rate of 20 kilonewtons per meter. So that is a slope such that it gets us down to about -8. Then the shear is constant for a little while because there's no distributed load, and then it takes a jump of 50 down, and then it's constant again with no load. So we go down to -58 there, and then back up. So with that, we know that our maximum shear concern is out here at the very end. But we have to do the same thing for moment because that generally dominates. Let me just back this off a little bit so I have some more room for the moment diagram. Okay, we can draw this real quick. We start at 0 moment because these are two simply pinned ends. So we know those points exist. This is what kilonewton meters. And then we have a positive slope that decreases to 0. We know that to be a parabolic shape. So we hit 0 right when the shear hits 0. Remember, the shear is the slope of the moment diagram. Then we continue off, curling over a little bit. Then we're constant for a bit, and then even more constant for a bit. So we got to sketch it in here. Looks something like that, I guess. But it's pretty obvious where the maximum is. It's right there. As would make sense because we know we have 0 moment on either end, and we have an enclosed area above on the shear diagram and a closed area below, and those two have to be equal, which would put the peak right there. And the area of either one of those is then the change in moment between those 2 points, which will give us the maximum moment. Coming back to everybody, I hope. And so that's a, where do I have that? That's 67.6 kilonewton meters as our maximum expected moment. All right, so with an allowable shear stress based on whatever material is expected for use for steel, for a stress limit of 160 megapascals, then find a section modulus and recommend a beam that would work best for it. And we are going to have to go to the SI tables because it's an SI problem. So Those are just a couple pages down. You just have to watch the fact that the things are in millimeters. So, in the 8th edition, that's page 804.
So it's a millimeter.
Yeah, it happens to be in millimeters. So we need to come up with a recommended section modulus. We now know the maximum moment. Remember, this is a minimum section modulus we're looking for over the allowable stress. So we have these numbers now. Just have to make sure that in the right units. Bless you. And notice a couple powers of 10 is taken off of the number in the column. If we do this in millimeters, it's going to be a very large number, so they didn't feel any need to put all those zeros in the column over and over. So they pulled 10 to the third out of the column. So figure out a section modulus, make sure the units work. And then recommend a couple beams, 3, 4, even 5 if we need to, just to make sure you got the right number of beams. Just to make sure you've gone through the catalog, pick the best possible beam. For those of you that don't have a book, I'll have to move this around as you need. Or scooch over with someone and take a look at their book, but you all need to know how to do this. Because if nothing else, we're going to revisit it on the final test. What now? Yeah, remember, the section modulus has units of millimeters, or length cubed. So you have to get this ratio, which you have units of length cubed. You have to get this down to millimeters cubed as the length unit, the base length unit, just because that's what happens to be in the table. I guess you can hand input this into a spreadsheet and make it into meters. Don't forget too that, or don't miss to notice that the weight is kilograms per meter. It's actually the mass per unit length, not the weight per unit length. So you have to make sure those units work as well. So everybody have a calculated section modulus? No sense going into the tables if we don't have that one right. Got something, Tom? In terms of 10 to the third millimeters cubed, because that's what we need to get into this table directly. So we'll need this front number times 10 to the third millimeters cubed. So whatever you give me, gotta have that already on there. Anybody have anything to offer? Phil? No, Tom? No?
422.5.
422.5. Okay, so now we can go into the table and look around. Notice these are way over the top. We need to come down quite a bit. Maybe we put the 632 in here. We don't know what, it could be there's a beam available below that. We don't know from the table. But it's free to write them down. Remember, we're looking for the lightest one. So go ahead and take that 632 for W41039. So that's the beam, that's the section modulus, 632. What else looks yummy? Take this 475 at the bottom. We don't know what's below that. Our table, they may or may not be a beam that's made like that. It's W36033. Now there may be other considerations, of course, cost, availability, the depth of these beams may be of importance. Depends on what kind of things you need to put in the inner space between the joists, if you need to run pipes or cables or something. So what are we looking at? Anything above 42.5. So here's 54.7, W31039. Oh. 475, 547. You coming up with the same beams as possibilities? Everybody's got their finger actually running down the table. Ken, what table are you looking at? Mine up here. David?
When I converted into millimeters cubed, I actually got 0.4225 for your.
Well,
Table's 10 to the third.
remember when you convert from millimeters,
You have to take that kind of
to
back.
meters, you also
Yeah.
have to cube this. You
Yes.
don't just write a cube down in
I
here.
think I did take that into account, and still got that.
Did others get this?
Okay.
Okay, so double check those, David.
Yes.
There's a lot of power of tens in there. So we just picked up the 54.7. This 535 here. 250, 45, 535. 50. What a memory. 250, 45, 535.
That answer would be right if it wasn't to 10 to the third, I should say.
Say what?
I would have, I guess would match mine if it was not, if 10 to the third was taken out.
Yeah. You gotta check that, something's,
Yes, I
something
checked.
is, cause,
Yeah, I
'cause
checked
others
that.
got this.
Yeah.
One last possibility, I guess, 583, the 259, 583.
There's also on the
46.
table with the same, because of the way they publish it.
Wait, we're not 46.
Did I miss one?
Well, I would go one lower, it's 440.
Oh, 4, 448, oh yeah. We're at 422. So we'd want the next beam, 46, 448. So you've gone through the beam catalog, picked out a couple possibilities, and chosen which one
360.
as a first step. Choose that one because it's lighter. Don't forget the value given here is kilograms per meter, not newtons or kilonewtons per meter. So you need to do a quick calculation of the beam weight, compare it to the total load. So the beam weight, we have a 5-meter beam and a 33 kilogram per meter mass, the mass per unit length, and then you need to multiply that by G to get the beam weight, and it comes out to be what, 1.6 kilonewtons, which is way less than the 110 kilonewtons we've got on here, barely over what, 1%, not even 2% of the total load. So this is probably more than sufficient. This 42.5 won't go up enough to go to the 47.5. So as a first step for us, that would be the beam to order.
Is there a certain fixed percentage that you want us to pay?
It depends. I don't remember if the factor safety is on, well, no, I don't even know. If the factor safety is already on this number, which it might be. You know, if you've got a factor safety of 2.5, this is way smaller than the beam can actually handle. Plus there are different materials used for these beams. Notice that there's nothing about the actual material of these beams. It's nothing more than the geometry of the cross-section that's in these tables.
Well, I think the kilograms per meter might specify material.
Yeah, well, the density would be in there, but who knows what that is.
Yeah.
Yeah, I guess the density would be in there, so. There are variations on this, I guess there's already less than that. So if anybody's got a smartphone, you can download the US Steel app and order these beams for us right now. No? No, nobody's going to. All right. Well, I guess kids are not as wired as reported. Because somebody should have done that already. You know, we could have these beams here by the end of class if somebody jump on it for us. Okay. So I'm going to leave one to you. I'm working way too hard. It's time for you to take over. All right. Look for a wide flange beam. That can support this situation. Uniform distribution of the load. And 1,300 pounds per foot. Over a 16-foot beam. So this section's 10 foot. The overhang is 6 feet. And the allowable shear stress is 24 KSI. Allowable shear stress, 14.5. Now, we'll just take the maximum shear and then divide it by the beam's cross-sectional area, which is also in the tables. We'll have to go back to the English tables, of course, but the cross-sectional area is right there in the table. You don't have to figure anything out, just compare the shear to what's allowable. All right, so recommend a couple beams, and then pick one. And then order, say 500 of them for us. And give me the purchase order. All right, so you'll need the maximum shear, the maximum moment. Fairly straightforward setup though. If you can find what the maximum shear, maximum moment are without doing the shear moment diagrams, you're welcome to. I can't do that as well. It's just a lot easier to do the shear moment diagrams, I think. So come up with the maximum moment, the maximum shear, and then recommend a section modulus. And then we can compare those. When you pick a beam, check the cross-sectional area of the beam, figure out if the stresses are below the allowable. Well, the section modulus will guarantee the normal stresses are, but you've got to check the shear stresses as well. You may just need to go to a beam with greater area. We've got to pay a little bit of attention to our answer, because there's kind of a subtle thing that happens in here with the shear. What's that?
So this is trying to take, I wanted to see what I can do if I was trying to take into account the linear density of the beam. Well, let's do it, right?
Chris, you have English tables on there? And so what you can do is print out the English tables for a small fee.
They're not getting convertible views.
You what?
They're not getting convertible views. Is that the thing?
Yeah. All right, I think most people have the reactions. Does that look right? Oh wait, 14, I didn't see the 4 at first. Round up a little bit, just gives you a little more conservatism in the value. For the maximum moment, maximum shear, if you can do it without the shear moment diagrams, more power to you. I can't. But if you're gonna do it by eyeball, you better get it right. You gotta get your units right. Because the area is in inches squared, the section modulus in inches cubed. So you gotta get all of it right. Okay. So. 4.2, and then it goes down at a slope of 1,300. Should do something like that, down to -8.8. And then takes a jump up of 16.6. And then finishes at 0. So that jumps up to 1.78. It's about right. And then the moment, let's see, we know at both ends there's no sustained moment. We know right here there's 0 slope on the moment diagram, and we have a bunch of curvy shapes in between. So we can figure out this area will be the change in moment here that'll give us the peak. That's 6.7. That area is 6.7. We can figure out how far down this takes us, and then this should bring us back to 0. So maybe something like that. So it gives you 2 points you need to check, and you can check them both probably most easily by looking at the area of the shear diagram above. Whatever this area is, which is very easy to calculate, will be this change, this delta M down to here. Or that'll give you the change in moment between the same 2 spots. We know we finished with 0 moment, so we can back up and get the maximum moment there. We know it's 6.7 there, and I think this comes out to be 23.4. We don't care too much whether it's compression or bending. We've got to protect for whatever the maximum is. So watch your units. And allowable stress, so we can recommend them a section modulus. Just have to get the units right now. But I'll leave that to you. Pick 4 or 5 beams again, just to make sure you've covered them. Because you may find that either the load is increased enough that the normal stresses become a problem, or that the shear is a problem, you need to go to a greater area. Your math.
I'm trying to take into account the linear time scale. I mean,
Don't make this more problem than it is. I like those kind of challenges, David. But we're trying to be a little more modest here at times. Phil, doing okay?
Yes.
So pick a couple beams that look good. A shear modulus that looks good. Watch your units. That'll kips cancel. We get square inches on the bottom, comes on the top. We get inches cubed, so that's good. And so remember, x-axis, we're looking for something that gets us just over 11.7 without going too far over, because you're just paying for beam you don't need. So we got a 14.9 there. 10.9's not good enough. Here's 11.8. Just skim by, good enough, we'll take it. Look, 13, 14. But you're giving away the answer already? Not making everybody else work for it? Stay boy. Okay, we can pick out a couple beans. Look juicy. It's fun. Everybody loves to shop. So that's what we're doing.
I want the 4-inch what?
14, yeah. So W12 by 14 has a section modulus of 14.9.
Red beams are more
Might want to
expensive.
write down the area on this one because we're going to have to check the shear stress. So that area is 416 and it's in inches squared. So that beam will do us. 13 to 10, 15, an area of 4.41. Might do us. Shop for a couple. You know, when you go into the gap, you don't just pull on one pair of pants, you pull out a couple, take them into the room, come out, let your mom look at them, see if they're okay. What I do, area 444. These are the same beams everybody else was looking at. Let's go down to the 6. Could be substantially lighter. Let's see. 10.2 is not good enough, 13.4 is good enough, 620, 586. Okay, same beams you guys picked? Give or take a little bit. And so the lightest one is that. So you can check how the weight of this, well, 14 pounds per foot compared to 1,300 pounds per foot. It's not going to be a big concern. But we can check the shear stress. Now here's the deal with the shear stress. Be careful with this, because this is the entire cross-sectional area of that beam. Remember, we're looking at I-beams. But as you may or may not remember when we talked about shear flow, the flanges don't really carry much shear. Most of the shear is carried by the web. So that's really the area then that we should use for the shear stress. So we check it for our beam. What is that? That's the TW by the D minus 2TF if we want to be really precise about it. So which beam are we on? 12 by 14. So we do the 11.9 times TW, give us a pretty good picture of what is going on. A bit of shears held by this part. So just to make the calculation more straightforward, I don't know much. We look at it as if there are no flanges when we calculate the area for the shear stress. So we take the maximum expected shear over the area of the web, excluding the flanges, and see if we're below the allowable shear stress. And that was what? The D times TW. So D for the beam we picked is 1191. TW is 2. Sorry, what was T? 0.2. That's 0.2 inches, 0.2 of an inch. Well, that's what it says. That's pretty darn small. It's less than 1/4 of an inch. Oh well, that's what it says. Kind of scary if you ask me. And we get 3.7 kips per square inch, and our allowable is 14.5, so we're okay. If it wasn't, we'd have to find a beam with greater area. So this beam doesn't add appreciably to the normal stress, and it's adequate in shear stress. And notice that this area that we're using is about half of the total area of the beam. It's actually there because there's so little shear held by the flanges. So we take them out of the shear calculation. And we get a pretty good picture of what beam would do us. Okay, everybody agree with most of those calculations?
That's the web.
this is the web,
Right.
and these are the flanges.
And it includes the little piece.
Yeah, just to make it, if you're borderline with this, then you need to really look closely, but don't design for borderline, don't design to just get by with these barely. Gotta put some margin in here so that you don't end up in court defending what you did. If you're cutting things that thin, you don't have a whole lot of defense. All right, any questions about this one? Okay, another way we can approach these kind of things that may help keep cost and weight down is for sort of a selective beam design. Imagine you have a problem like this, simply supported beam, but and that's an 8-meter beam, and we'll make it simple. I don't want the load to be a big deal with this. Point load right in the middle, expected of 500 kilonewtons. But here's the thing, happen to have in stock, so we want to use these. You know, somebody bought way too many of these, so now we got to use them. Some W690 by 125 beams. Now, I don't believe that's actually one in the book, but I'll give you the information we need for it. Could be that it's in the new version. No, we only go up to 610, so this is a bigger beam than our book happens to have. So somebody bought these, you know, got them on eBay, real cheap. Now we've got to use them, but here's the deal. Cross-sectional area, 16,000. Section modulus is 3510. And then remember that's 10 to the 3rd millimeters cubed. And cross-sectional moment of area 1190, 10 to the 6th. All right, so for whatever reason, there's the beam we've got. The trouble is, it's adequate for the expected bending moment. Remember, we've done this type of problem before. So the moment diagram, well, the shear moment diagrams are very easy to draw. Because of the symmetry of the problem and the fact that it's only a point load. The trouble with this beam that we have to use, because the boss wants to get them off the inventory, so that maximum moment comes out to be minus 1,000, or not minus, but 1,000. And that's kilonewton meters. The trouble is, with this beam, if you calculate, an allowable normal stress, just like we had before, 160 megapascals, that this beam is adequate for only a certain portion. In the middle of the beam, there's more moment here than this beam can support. Looks something like this. So for this portion out here, the beam is okay. but there's greater moment than this beam can support. So what we're going to do is we're going to look into inventory, and we're going to weld some plates on, just in the center where we need the extra protection. So that'll make the cross section of the beam, which might look like that. We're going to weld some plate on, because we also have that in inventory, and it's 16 millimeters in thickness. We've got lots of this plate. We can make it as wide as we need to. So we need to add enough plate to protect for this worst case point right here in the center. That'll overprotect the rest of the beam, but there's no sense going any farther to the ends because that part of the beam's already protected. See the picture then? So we've got this tail end of the beam. Now we're going to put on a plate that will protect the rest of the beam. In fact, it'll overprotect it for those shaded portions. So your job is to find out how wide the beam should be, this B, and the plate should be, and how long it should be, L, which is fairly easy to do. Just find out where these the points are that the moment diagram goes over the exceeded allowable part that we could protect. Everybody see the picture? So when you do this, when you look at MC over I, you're going to have to recalculate a new moment of inertia for this center portion where we've added these plates, because we now have all of this added area with these extra 16 millimeter plates that we've welded on. So we're getting close to the end. I'll give you the skeleton of the solution. Turns out this portion here is 2.24 meters. So that tells us how long the plate should be. But now you need to find how wide the plate should be to handle the rest. To do that, we need to find out, remember that the section modulus is I over C. C is increased now because of the extra plate, but so is I, so we need to figure out what those are. And this has got to be such that it handles the maximum moment expected right in the center of the beam, that 1,000 divided by the allowable shear stress of this particular steel. So we can put all those pieces in. Remember that C increases by 16 millimeters. And so we need to increase the moment of inertia by, actually we need to be greater than that, so let's write it that way. We need an I that's greater than this MC over allowable. MC over sigma. That turns out to be 222 times 10 to the minus 3 meters to the fourth. remember that's partly made up of the moment of inertia of the beam, which is right out of the tables. Well, no, we don't have them in our tables, but I gave it to you. It's just that number right there. Plus the fact that we've welded on these two plates, top and bottom. The moment of inertia of those is easy to figure because it's just a simple rectangle. So it's 1/12, yep, using the same thing, B, H cubed. Where H is given, it's the 16 millimeters, but B is not. You're looking for that, so you're going to have to solve for this. Plus, don't forget 1/2 AD squared because these plates are off of the neutral axis. So that will be a function then of the unknown B, and you can solve for it. So we'll know how long the plate should be. We got that just from the moment diagram so that we know what part we haven't protected with the regular beam, how much extra we need to protect, and then we have now the width of these plates. And you should get then about 267 millimeters.
You know how
So that was real quick, just because we're at the end. Yep.
You know how tall the beam is?
Oh, sorry, there it is. Yeah, it's 678. So that's this distance. 678 millimeters. Okay, and your boss is going to love you because not only have you used the beams that somebody bought in excess, but you've also used up all that extra plate that was lying back behind the last warehouse.
Glue it on.
What?
Glue it on.
Glue it up? You might want to weld it. Super glue it. You work for that guy with the helmet. All right, that was quick at the end there. See if you get the same things.
Are we gonna do another one of those?
What?
Are we gonna do another one of those?
Now? No.
No.
We're off duty now.
Okay.
Ever? That's one, you could knock that out in about 12 minutes on an exam, I think.